Hello, everybody, and welcome. My name is Sam, and I'll
Hi.
be your host today. Welcome to Astronomy Days, and we get to talk about the James Webb Space Telescope today, which I'm very excited about. We have people joining from YouTube and Zoom, so I have a quick tutorial on how to use Zoom. But while I go through this, I have a question for you all. If you can point a giant space telescope at anything in the universe, what would you like to observe or discover or explore? Okay, so while we are going through this, in Zoom here, you'll see the option for muting and unmuting and starting and stopping video. We are not going to have the option of doing that during this program, but you'll also see the option for closed captions here. And if you click on that, you can get closed captions. You just click show subtitle, and you can go through this menu to either make subtitles really big or really small, whatever your preference is. To best view our speaker's presentation as well as his video, if you'll click, go up to the top, go to speaker view, and then also under view options, do this side-by-side mode. So you'll see the presentation and the speaker's video there. And you can adjust the little slider to make the presentation bigger or the video bigger, whichever one you would like. And finally, both in Zoom and YouTube, we do have a chat. So please feel free to type up questions and comments and relevant observations to what our speaker will be talking about today. Please remember to be a good digital citizen. So keep your comments on topic, and as well as being respectful of both your participants and the speaker today. All right, and with that, I would like to introduce our speaker. So talking to us about the James Webb Space Telescope today is Alan Rich, and he's one of our fabulous JPL Solar System ambassadors. So thank you so much for speaking with us today, Alan.
Thanks for having me here. And thanks for everybody getting up at the wee hours of the morning like this to come and hear me talk. It's early. So I got my coffee mug here. I love the smell of rocket fuel in the morning.
Perfect.
And sniffing rocket fuel, that'll wake you up, but almost as good as coffee. So do you want me to get started?
Yeah, go ahead. And yeah, if you can share your screen, that'd be great.
See, I'm a little slow this morning.
Oh, no worries.
I need to get more of this coffee inside.
No worries.
Okay, here we go. I have host disable participant screen sharing.
Uh-oh, that's not a good thing. Hold on a second.
Okay. Say when.
Let's see. Trying to see. Oh, okay. I think if we can make you a co-host in the meeting. I don't know how you lost the co-host, but perfect. Okay, you should be able to share now.
Okay.
And while we're waiting on that, we've got some awesome responses to our question of what we would study in the solar system. So we've got Calypso, the Horsehead Nebula, they want to study. Also, oh, Europa would be great too. That would be fun.
Oh, yes. Good answer.
Yeah. Are you able to share?
No. I'm going to stop this, and it didn't bring it up as an option. It's be a good time for questions.
Yeah, no worries. We've also got Goldilocks Zone. I don't think I've heard of the Goldilocks Zone, but that would be fun.
Yeah, the Goldilocks Zone, that's a good thing. That's for exoplanets, alien planets that it's named after Goldilocks because, you know, the Goldilocks and the Three Bad Bears story.
Yeah, so it's like the perfect place.
The bears go in and there's some pizza that's too cold and there's some pizza that's too hot. And the Goldilocks Zone is, well, Goldilocks, you know, pointed out to the bears.
Yeah.
The perfect, well, okay. Let's try this
Perfect.
again. Okay, here we go.
All right, cool. So we are seeing your presentation.
Okay.
And there we go. It's in full screen now. Awesome.
Okay.
Sorry about the technical difficulties. All right.
That's
We're good to go now.
Probably my fault.
No.
Okay, James Webb Space Telescope. What we're talking about today, the new telescope. There's a couple of things I'm going to focus on a little bit. It has a weird, crazy way of flying in space that's not really orbiting things. And it sees things that we can't see with our eyes or with binoculars or with telescopes. I'm going to tell you how it does that. But as you probably know, the James Webb Space Telescope is the newest, biggest, and greatest telescope ever made. It was launched a little while ago and has just recently reached its place where it's going to stay in space. I'm going to tell you about that. It replaces the Hubble Space Telescope, sort of, but it's a lot better. The Hubble Space Telescope was just absolutely amazing what it did for us. Like, look at this picture right here. You guys have probably seen this. It's called the Deep Field. Well, there were a lot of these. This is a Hubble taking a picture of the piece of the sky that is 1/13 the diameter of the moon. So it's like if you took a pea and held it in your fingers up into the sky. That's about the size of the sky that Hubble looked at to take this picture. But all this stuff that's in this picture, these are, I think there's like one star in this picture, and the rest of this, everything in this picture is galaxies. Not just stars, but entire galaxies. And each galaxy has billions or trillions of stars in them. And the mind-blowing thing about this is that since we're looking for alien planets around alien stars, or exoplanets, we call them, galaxies, we think that just about maybe almost every star that forms, it's a normal part of forming a star to have a solar system with planets in it like ours. And you look at this picture and just a tiny piece of the sky, you've got all these galaxies, and each one has billions and trillions of stars, and each one of those has a solar system with planets. So there's just planets like so many you can't even imagine. I mean, you would never, if you were like in any one of these galaxies, it's hard to even envision what millions and billions, well, millions maybe, but billions, it's hard to even envision what a billion is. But if you had a super fast spaceship and you were to go into one of these galaxies, and you could, every few minutes, you could just go to another star and look at their solar system, and you could visit hundreds of stars every day your entire life. You wouldn't even come close to visiting all the stars in just one of these galaxies. And that's in your whole lifetime. Of course, well, I guess you can't count when you're a baby, because babies aren't interested in space exploration. So you'd have to wait a few years before you started it, until you're not a baby. But other than that, it's just the numbers are enormous. The chances of habitable planets are just overwhelming. And this was Hubble. And the James Webb Space Telescope is going to be able to see so much more than even this, because we've only, even with Hubble, we haven't even seen most of the universe. And the James Webb Space Telescope is going to be able to take us back. It's like a time machine. It can see light, like all of these galaxies. This is not the way they look today. This is the way they looked millions of years ago, when the light from them started its voyage to us so that we can see them. But the James Webb Space Telescope is like a time machine back to almost the beginning, almost the Big Bang, the beginning of the universe. It'll be able to see so many more things, and it's just going to be goosebumps when we see what it sends back. It's going to be amazing. Oh, now what? Why do my buttons not work? Okay, here we go. James Webb Space Telescope, it's a big thing, and this is a model of it at NASA's Goddard Space Flight Center, a life-size model of it. It looks like a Star Wars Star Destroyer or something. But most of that on the bottom is those layers of gray things. Those are heat shields, because the James Webb Space Telescope, it needs to stay really cold. I'll tell you about why that's true in a minute, but I just put this picture in here with this life-size model of it and all the people that worked on it to show you that this is a monstrously big spacecraft that has just arrived where it's going. And the first problem is that this is the rocket. This is the European Space Agency Ariane 5 rocket that it was launched on, and it's not a terribly huge rocket. But the James Webb, that huge thing that I just showed you, that's unfolded. And it fits up, it has to fold up and fit up into that nose cone area at the top of the rocket. And then because of that, I mean, you can't launch something that's this size of a Star Wars Star Destroyer into space. You got to fold it up. And here's a cool story. The solar panels in a lot of our spacecraft, this is a totally random thing that popped into my head, cool story. The solar panels that our spacecraft have that have to be folded up for the same reason. You can't just have extended solar panels on a rocket like this, launching it from the ground to space. So it's always a problem when you get into space. All that stuff has to unfold, and all the little mechanisms and mechanical things and motors that unfold everything. And this James Webb Space Telescope is the worst ever. It's just so many parts that had to be unfolded right, tucked into this little rocket, the top of this little rocket. But it's always a problem with these solar panels as they unfold. And a brilliant revolution in spacecraft solar panel folding came in a Chinese restaurant in Pasadena, California, where two engineers, NASA engineers from NASA's Jet Propulsion Laboratories in Pasadena, were in a Chinese restaurant, and they were playing with those little Chinese fans that unfold like this. And one of them's like, oh, this is how we're going to do solar panel deployment in space. So, cool story. I like that story. And this is an artist rendition of the fairing at the top of the rocket coming off of the James Webb Space Telescope. And, and you can see it all folded up in here. There were actually, in unfolding the telescope to get it into operating configuration, there were 344 single points of failure, which meant that, I mean, this is a terrifying number if you're a spacecraft engineer. 344 things, little actions that could have gone wrong, and it would have ruined the mission. They all had to work. And that number is like, for the Mars rovers, it was like less than 100, something like that. And for this one, it's 344. And because it's not in Earth orbit, the Hubble Space Telescope's in Earth orbit, and it had a couple of problems, and astronauts were able to go up and service the thing. This one is not in Earth orbit. I'm going to tell you where it went, but it's so far away that if something goes wrong with it, even in the deployment to where it'll work at all, or if it runs out of fuel, or if something breaks, it's too far for astronauts to, even if we had space shuttles working, it's too far for astronauts to go. This is a picture of James Webb all folded up and ready to go into the rocket. Why is this? Okay. Unfolding the Webb Space Telescope. I told you 344 critical ways it could go wrong. It just arrived just a couple of days ago where it's going, and it's not going to be sending us any pictures for about 5 months, because this whole procedure here of unfolding is part of it, and it has to cool down to over 300 degrees below 0 Fahrenheit, and it has to get all of its instruments calibrated and tested, and the aim correct, and largely cooling down too, and all these tests that have to be done. And that's going to take up like 5 months. Just after it got to where it's going, it's going to take like 5 months to get it ready to take its first pictures. Okay, now, thing number one that's cool, where it went. It's called a Lagrange point. And this is a graphic of the sun in the middle and the Earth, the little gray circle, and the moon over there on the right side. And what a Lagrange point is, it's super cool. And another name you might hear people talk about it is gravity surfing. It's not just going into orbit like regular rocket science and going from one planet to another, going to Mars or something. It's like there are these places in space where there's two big things like the sun and a planet, and in this case, our sun and the Earth, that they both got gravity. And the sun is a lot bigger and heavier, so it's got more gravity than the Earth. So there's a place, if you can just picture this in your head, there's 5 Lagrange points with the Earth and the sun. And one of them is really easy to picture. And it's kind of intuitive, and I'm going to tell you that one. And I'm not going to try to explain 2, 3, 4, and 5 because they're real hard to envision. But number one is like you got the sun and the Earth, and each one of them has this gravity. And you can picture that somewhere between the Earth and the sun, there's a place where the gravity is kind of equal. And it's going to be closer to the Earth because, like I said, the Earth is smaller and less massy and doesn't have as much gravity. But if you find that point and you put a spacecraft there, it's just going to kind of float there and not go anywhere. It's not really orbiting anything. It's just kind of floating in a space in the weird little place that the gravity of two big bodies, like a star and a planet, are kind of equal. And that's Lagrange point 1. And that's the one that's easy to understand. Now, the James Webb Space Telescope is going to Lagrange point 2, which is on the other side of the Earth from the sun. And it's really hard to envision how that works. And Lagrange point 3 is on the opposite side of the sun from the Earth. And it is always directly opposite from us. And a lot of science fiction stories say, you know, if you put something in Lagrange point 3, it's just going to kind of float there. And if there's a planet, a lot of science fiction has envisioned planets being there, like the undiscovered planet. Because if there's a planet that's always exactly on the opposite side of the sun from where we are, we're never going to see it unless you take a spacecraft out and go to the left or go to the right. Then, oh, there's a planet back there behind the sun. But so a lot of science fiction stories pretend that there's a planet back there, but we know there's not. Lagrange point 2 is where the James Webb Space Telescope goes. And look at these Lagrange points 4 and 5 out here to the left and the right of the Earth. I'm not even going to begin to ask you to envision how that works, but it's points in space that are kind of have this gravity thing going on between the sun and the Earth. And there's dust and asteroids and things that are just kind of trapped in there that follow us, that are ahead of us on our trip around the sun on Lagrange point 4. And Lagrange point 5, they're kind of following us. We're kind of dragging them along, this dust and these asteroids and things. This is just crazy, bizarre. But gravity surfing, one way to fly in space. And there are all these points around any two big things in space. Any planets or even a big asteroid is going to have these Lagrange points. So if you map like this looks kind of like a weather map of temperatures over like North America. If you were to map gravity in our solar system, you would see all this stuff happening between everything, between the sun and Earth, the sun, Earth and Mars, Earth and everything, everything and everything. So you're going to have these lines everywhere. And this is kind of a little cool thing. It would be theoretically possible to launch a rocket. And you remember one of the things we call this is gravity surfing. It would be possible to launch a rocket if you did it just at the right time and at just at the right speed, that rocket would go up, and without ever touching a rocket engine again, it could gravity surf through our solar system and visit every single planet, every single moon, every single anything that's big enough to have any gravity without ever touching a rocket engine again if you launch it. The problem with that is that one perfect time to launch it happens once every few millions of years. And the trip through the solar system is going to take millions of years. So we're not going to do that, but it's a kind of a cool idea, and it's theoretically possible. This is another picture of the Lagrange points, and over on the far left, L2, there's a little picture of the James Webb Space Telescope. And these Lagrange points are not incredibly stable, so the Webb telescope is going to have to make little rocket correction burns every now and then. And at launch, there was enough fuel loaded on it to where it would be able to maintain Lagrange point 2 for about 10 years. But the launch was so perfect and so accurate to deliver it to Lagrange point 2, like bullseye, that we'll have enough fuel to keep it alive and in place for about 20 years, which is very good news about the launch. Launch went very well, bullseye shot right to where it was going. And it's about 1 million miles away, Lagrange point 2 is. That's about 4 times further than the moon. And this is a little bit nicer picture than those last ones. It kind of shows where it is. Again, four times further than the moon. No, not in, I don't know, unless SpaceX decides they want to go do a service call to the Webb. There's probably no way in the next 20 years that there's ever going to be a manned mission out that far to fix it. We have used, you might say, well, Alan, this gravity surfing is weird. Have we ever done that before? Yeah, we have. The Lagrange point 1, remember the easy one to imagine, we had a spacecraft there right now. And in fact, we might be talking to it. So no, we're not. I'll show you this back here behind me in a second. This is our deep space network of radio telescopes and what we're talking to. We are actually talking to the James Webb Space Telescope right now, and I'll show you that in a minute. But about 20 years ago, we had a mission called Genesis that went out to Lagrange point 1 and just kind of floated between the Earth and the sun for like a year. I think it was about a year, and collected some of the outermost particles of the sun. And SOHO is there now. There have been a few other spacecraft that have parked at Lagrange point 2 before. I've got the names of some of them there. We don't have time to go into any of that. Lagrange point 3, I was telling you, nothing there as far as we know, but we've never really seen there because the sun's always in the way. So there could be a hidden planet behind it. There's not. And I talked about Lagrange points 4 and 5, where some dust and some asteroids are following us around as we go around the sun. Okay. Now, how does this thing see what we can't see? If you go back to before we figured this kind of thing out, and all we had to do was look up in the sky with our eyes, and then somebody made crude little telescopes back in the days of Newton and Galileo and those guys with the long curly hair. That's all you saw was things in the electromagnetic spectrum in the visible range. You saw things that were white, blue, green, red. But if it didn't have a color that you think of when you get out a box of crayons, we couldn't see it. No matter how big your telescope was, if something didn't shine blue or red or green or white, we weren't going to see it. And the vast majority of everything out there in space doesn't show up as green or blue or red or white to us. We can't see it at all. So once scientists figured out, well, it may not, it's like if you're a doctor and you're at home at night and you realize that you left your x-ray machine in your office on and running, and you needed to go back and turn it off. And you went back to your office and you can't find the light switch, so it's pitch dark, and you're fumbling around with your hands trying to find your x-ray machine to turn it off because it's blasting the neighborhood with x-rays. but you can't find it because it's totally dark. Can't see it. But it's emitting X-rays. If you had taken an X-ray counter in there with you, you could find your X-ray machine, even though you can't see it in the colors that it gives off if the lights are on. And this is kind of the same way. We're looking at things that give off X-rays, ultraviolet, infrared, gamma rays, but they're giving that stuff off, but they're not giving off any blue or green or white. So once scientists figured out, let's look somewhere else besides colors and things, then the universe just opened up, and millions and millions and millions more times stuff we could now see. Distant galaxies, all kinds of things. And the other thing too is there's that thing, it's a little kind of physicsy for this, but when light travels a long distance for a long time, it redshifts, and if it once was back towards the beginning of the universe, if it once was stuff that's green or white or blue, once the light has traveled to us to where we can see it, and it's been coming at us for billions of years, the light redshifts out of the visible range of blues and greens and yellows and things into infrared, which is more like heat. So what really is out there shining green and blue and white and yellow and stuff, not anymore by the time the light gets here. So we can't see it. But if we look in infrared and realize that this infrared here used to be red and green and yellow and blue, then we go, aha, there's some more stuff to look at. Okay, so infrared is, I should probably go to the electromagnetic spectrum like this. You see over the bar here, there's the visible range, the reds, greens, blues, yellows, all that. And on either side of that is stuff that we can't see. Radio waves, microwaves, gamma, X-ray, ultraviolet. And we've done this before. The Hubble Space Telescope mostly sees in the visible range. James Webb is going to look mostly in infrared, because that's what I was telling you about the redshift. That's where you want to look if you want to see things that are super, super far away, like towards the beginning of the universe. And the Spitzer Space Telescope, I'll talk about that in a minute. We've had other space telescopes that have done this before, but the James Webb is going to look in infrared specifically. Well, one reason, again, to see things that are really, really far, far away from the beginning of time. This is just another graph of the electromagnetic spectrum, and shows like microwave radiation that you cook food with, cell phones, FM radio, AM radio, all that stuff is not, we can't see that stuff. It's not in the visible range. And then you go, what, the ultraviolet that gives you sunburns, nuclear power, cosmic rays, X-rays, the really dangerous kind of radiation in space, all over there on the far right. Can't see it, but it's real useful. Okay, so a couple of months ago when I was thinking about doing this presentation for you guys, I'm like, well, how many space telescopes have we put up into space? And I'm like, I didn't need all of my toes and fingers to count them all that I could think of, but it turns out I would have needed to, if I'd really known, I would have had to get several other people around to use their fingers and toes too, because there's been like 115 space telescopes sent up. Way over here, this is the same electromagnetic spectrum chart I showed you a minute ago, what we're looking at with these space telescopes. Way over on the left, it's kind of backwards from that other one. The nasty stuff from space is on the left here, and things like microwave radiation and radio waves and things are on the right. But in gamma, there have been 16 space telescopes, 6 of them from NASA here in the United States, that Compton and Swift are a couple of examples. X-rays, there have been 38 X-ray space telescopes, 17 of them from NASA, like Chandra and Compton. Ultraviolet, Hubble could see that, Swift and Galax, 22 missions, 15 from NASA. In the visible range, the boring ones, 12 missions, 4 of them from NASA, like Hubble, Swift, and Kepler, the Planet Hunter, which is my favorite space telescope because it's the one that looks for alien planets. If I have time, I can tell you how it does that, but it's in the visible range. And Kepler has found like 4,000 alien planets so far. And microwave, 4 missions, infrared and sub-millimeter, 12 missions. So you can see we've been doing this for a while, and you can look at anything. You can look at gravity waves, electrons, cosmic rays, anything you can't see. You can make a telescope for it to specifically look for it. And we've done that 115 times. This is Compton. A lot of our space telescopes, the reason why I couldn't think of them is because I'm kind of into rockets and launching things into space. And a lot of our space telescopes, because they're so delicate, were launched aboard the space shuttle. It's kind of a smooth, easy ride because we got astronauts in there and they don't like things too fast and bumpy and crazy. So a lot of our space telescopes actually went into space. Hubble did, the big one, Hubble, in the cargo bay of a space shuttle, where it got a nice, safe, smooth, easy ride. Compton, gamma and X-ray. Chandra. And if you look at these space telescopes, they kind of look like Earth, like the big, nice Earth telescopes that you might buy to put in your backyard. They look kind of like big versions of that with solar panels on them. And it's kind of they are. Here's Hubble, actual picture of it. I think this was from a service mission where an astronaut took this picture while he was fixing something that was wrong with it. Galax, UV. Swift. The Swift Space Telescope could look at gamma, UV, or visible. So some of them can do more than just a narrow little, one thing at a time. Kepler, the planet hunter. You know how this works? Kepler, and one of the reasons why you have to put planet hunting telescopes like Kepler in space, because if you've got a telescope on Earth and you're looking at the stars at night and trying to look at planets orbiting those stars, it's just, there's so little light and they're so far away that you have to point your telescope at them for months or years at a time. And of course, that's impossible on Earth because the Earth is rotating. Like, oh, it's daytime. It was daytime about 8 hours ago. Now it's dark. So the sky is constantly moving across the sky. And you can't keep, at the beginning of nighttime, you point a telescope at some stars, and then 6 or 8 hours later, the sun's coming up and they've moved all the way from over there to over there. So that doesn't work. You have to point at the same place for months or even years at a time. And the only way you can do that is if you've got a space telescope that's not on the ground, not on the Earth, and you can just point it at some place you want in the sky and leave it there for months or years. So that's how the Kepler worked. And the really cool way it worked to find exoplanets is if it's staring at stars, if there's a solar system there, which it finds probably all of them do have solar systems, and there's planets orbiting that star, when that planet orbits the star in between us and the star, the planet kind of blocks out just a little bit of the light of the star as it passes in front of it. And that makes the star blink a little bit. And if aliens from space were looking at us now, looking at the Earth and the sun and the Earth and trying to figure out if the sun had any planets, the Earth would do that. It takes us 1 year to make a trip around the sun. So once a year, our sun, the aliens that are watching us would look at our sun and say, the sun blinks once a year. That's a planet there. And it would be us. Yay. So that's how Kepler worked. Found so far 4,000 planets like that. NASA has 4 telescopes they call the Great Observatories: Hubble, Spitzer, Chandra, and Compton. And if you look there, they're not all. Hubble's really the only one that looked in the visible range to see what we could see with our eyes and our optical telescopes. 115 space telescopes, 56 from NASA. I think I told you about this before. The James Webb Space Telescope is really a time machine, because if you look up at the sky, you're not looking at I mean, this is kind of a mind-blowing thing. If you look up at the sky, you're not looking at what everything in space looks like right now. Like the sun is 7 or 8 light minutes away. So if the sun actually, the fastest thing is light, which is what you give off to be seen by somebody else with eyeballs. So if the sun actually went dark or blew up 4 minutes ago, we're not going to, when you look at the sky, that's the way the sun looked 8 minutes ago. And if the sun blew up 4 minutes ago, we're not even going to know about it for 4 more minutes. And the moon is like, a second away. So that's what the moon looked like 1 second ago, not what it looks like at the exact moment you're looking at it. And the stars are crazy. The closest star is like the way it looked 4 years ago. And most of them are dozens or hundreds or even thousands of years, but they're all out there in this galaxy in different places. So you look up at the sky and that star, that's what it looked like 100 years ago. And that one right next to it, that's what it looked like 1,000 years ago. And that star that's going to blow up, Betelgeuse or Betelgeuse, or however you say it, the one that's about to blow up, it could have already blown up because it's so many light years away. Astronomers are looking at it and go, oh, that thing's about to blow up. So it might have already blown up, and we may not even see it blow up for another couple hundred years because that light from its explosion is traveling to us at light speed. Okay, James Webb, largest, most powerful, and coolest, literally. That means because it's looking at infrared, these heat shields here, the biggest part of it is shielding it from the heat of the earth and the sun, because this thing has to operate at like 350 degrees below zero. And any little bit of heat from the earth or the sun is going to make it just, it won't be able to see what it's looking for, because light coming from 13 billion years ago is so weak that it can't have any warmth around it to interfere with that signal. Here's a picture of the mirrors, the big golden mirrors. And it kind of tells you there's a couple of little people in that picture too. And it shows you, how big of this thing is compared to people in clean suits. And here's another picture of the main telescope assembly. And that you can see the guy down there at the bottom, a couple guys in this picture. It's a pretty big space telescope. There's some more people in there. There's a guy. And there's no heat shields here with this. This is just the telescope itself. And it's kind of, these mirrors are so perfect that whenever you take pictures of, a lot of pictures of them, they reflect like the inside of the room on the other side of the room. And you look at them and you go, if you're not real careful with how you do your photography, you're like, well, there's a picture of the side of the room. Oh, that's the mirrors on the space telescope. And there's another artist's picture of what it's looked like. And this is kind of like in space, you see the bottom right here, the brightness from the sun, and the brightness of the sun comes up and hits those insulating panels, and the actual telescope itself is on the other side, in the dark side. And there's like it's like 350 degrees below zero where the telescope is, and it's like almost 100 degrees Fahrenheit on the sun side. So there's over a 400-degree difference in one side of the James Webb Space Telescope and the other side of the scope. JPL, we don't really have anything to do with this, but except communicate with it. And I was wanting to show you that here. This was Goddard Space Flight Center and a couple of other NASA centers that do different things. JPL is mostly interplanetary robotics, like the helicopter and the robots we have on Mars. So, but JPL does do all of the communications to most of the world's spacecrafts. And this is just outside of Los Angeles, Jet Propulsion Labs. It's managed by the California Institute of Technology. And there's the guard from the front gate. He's missing a leg there, isn't he? Okay, so let me show you back here.
Yeah, and are you going to pull up when we're talking, how we're talking to this telescope?
Yeah, oops, it just went away.
Nope.
If we could get well, I have to enter a password.
Yeah, no worries. While we are doing that, we had a couple questions. Eleanor and Blair were wondering why one side of the telescope has to be so cold, which kind of went over is that infrared telescope just needs to be really, really cold to be able to read the infrared, the kind of heat signatures and the other things that it'll be discovering. And then we also had a question if for the James Webb Space Telescope, are there any particular regions of space that we're going to be focusing on, to aim the telescope? Or is it just going to be just kind of a broad overview of what we can see?
That's a good question. It will be specific things. And just like any of our space telescopes, this is just kind of the way it works. We're launching the space telescope, and it's got so many hours a day or so many hours a week or a month to look at things. So NASA asks the astronomers and the scientists around the world, what do you want to look at? And then NASA looks at their proposals and goes, ooh, that one's stupid, or that's a good idea, or yeah, this guy's got a good idea. Give him 5 hours next month. And so it's all kind of plotted in and written on a whiteboard, literally, like the this scientist from Italy gets it for a week next year, and because he had a really good idea. So people actually compete for time on any of these space telescopes, and a lot of our missions are like that are the rocket people that and the spacecraft people that put them up, they don't care. They put it up and they're like, okay, look at stuff. So then there's people that are like, okay, who's going to look at what? So they sort through these ideas and they allocate chunks of time. So
Great.
To screen share me and this monitor I've got behind me, could I do share screen? And maybe, yes, I think so. Okay, do you see me?
We see, yes. Yeah,
large?
we see
Okay, good. This is our deep space network, where this is the live monitor of the deep space network. It's in, and this is pretty cool too. We've got 3 sets of dishes, radio dishes, that we use to communicate with most of the world's spacecraft, not just the ones from NASA in the United States, because we've got this deep space network and we're the only people that can do it. There's 3 sets of dishes, and they're positioned at 120 degrees around the Earth, so that Mars is over here, but we've only got 1 set of dishes. Once the Earth rotates around and that set of dishes is pointing in the deep space on the opposite side of Mars, we're not going to be able to talk to Mars. So we've got sets of dishes positioned 120 degrees around the Earth, so that no matter where the Earth is in its day-night rotation and what you want to look at, we'll always have a set of dishes pointed there. And there's some in Madrid, in Spain, and there's some in Goldstone, which is out in the Mojave Desert near Los Angeles. And there's some in Canberra, Mexico. Canberra is in Australia, in Canberra, Australia. So, and if you look right down here at the bottom, JWST, the James Webb Space Telescope, and you see these little, I don't know if you can see it, but if there's little squiggly lines coming out, that means that there's signals coming in and out. So we are actually talking to the James Webb Space Telescope right now through Canberra, Australia. And another cool thing about this is that you can, if you figure out how to scroll. Oh, there you go. For anything we're looking at, like in Goldstone, we're getting ready to talk to a Mars robot, one of our Mars robots here. So it's lit up. There's no signal coming in yet, but it's going to come into the Mojave here pretty soon. We're going to be talking to probably robot Perseverance on Mars.
Yeah.
But James Webb Space Telescope, you click on that, and it is 1.4 million kilometers away from us right now. But here's the cool part. The round trip light time is 9.35 seconds. So signals back and forth to spacecraft, whether it's Mars robots or telescopes in the Lagrange point 2, they travel at the speed of light. And the really important and cool thing about this is why our Mars robots have, James Webb Space Telescope wants to tell us something. It takes over 9 seconds for that signal to get here. Like if something happened and it shut down or went into safe mode, or if it's got some pictures it wants to send us of something to take pictures of, it takes 9 minutes for that signal to get here. And then if we have to do something to respond to a problem, it takes 9 minutes for our signal to get back out there, 18-minute round trip. And that's with Mars, it's even worse. Let me show you here. If we go to this is our Mars robot, Mars 2020 Perseverance. It is 329 million kilometers away from us right now. And it takes light, the round trip light time is 36 minutes. This is why our spacecraft, especially the ones that go beyond the moon, have to have some level of artificial intelligence or autonomy to be able to do things themselves without some nanny at mission control at NASA going, turn left, stop, don't drive into that ditch, stop, don't do this, do this. We can't do that because the round trip light time is right now almost 37 minutes to Mars. So a robot could be about to drive off into a ditch and it sends us a signal saying, here's a ditch I'm about to drive off into. And we won't get that signal for 18 minutes. And then somebody at mission control is going to panic and take a little time going, oh no, should I tell it to turn left or turn right? Oh, turn left, turn left. That turn left signal is going to take 18 minutes to get there. So that's too long. It's going to be in the ditch already. So because of the signal distance and light speed like this, everything we put way out into space has to be able to make some decisions on its own and work without humans just really intervening all the time. And you certainly can't joystick control it like you could do a remote control car in your yard. You sure can't do that. So this, anything in space here, you can tell how far it is and what the light distance is.
All right, thanks so much for showing that to us. And I did put a link for that Deep Space Network Communications in the chat. So people can also check that out and see all the cool things that are communicating with our satellites and things now. Okay, we have other questions just about like kind of the build of the James Webb Space Telescope. We had a question about like how long did it take to build the telescope?
Oh, that's the answer to that is real embarrassing. Because it was started a long time ago. Like, I don't remember exactly how long. It was over 10 years ago, and there was a lot of problems. There were like technical problems that, oh no, that's not going to work. That part, we're going to have to redesign that part, or it went over budget and Congress is deciding to cut the budget, but don't do any more work on it until we decide whether we're going to give you money to finish it. So there were a lot of little problems, both political and budget wise and technical. So it took a ridiculously long amount of time to get this thing built. It's over 10 years. I don't remember the exact number, but we've been people that have been looking forward to it. Scientists are really super excited about it because Hubble was so awesome, and this is going to be awesome times 10. And scientists are just so excited about it, and we're like making jokes like, if it ever goes up, and they're, well, when James Webb Space Telescope goes up, we'll be able to see. If it ever does, it's never going to get there.
But it did. And I was so excited when I got the push notification that it was like, hey, James Webb made it to the Lagrange point.
Yeah. Surprise. It worked.
Yeah, it worked.
It's there. Am I dreaming?
Success.
Pinch me. So
yeah. And then we also had a question. What are the sun shields made out of that it can like block that heat?
Captain, I think it's like gold-plated Captain. It's a special material that in spacecraft, thermal management is a really big thing because there's a hundreds of degrees difference in temperature in space because of the way physics works in space compared to down here on the ground. You know, you put a spacecraft out in your garage, out in your driveway in the middle of summer, and obviously, yeah, the part that's the sun's hitting is going to be hotter, and the part that's on the bottom next to your driveway is going to be cooler. But in space, the way the physics works out there, there's literally 300 or 400 degrees difference in temperature between the side of your spacecraft that's pointed towards the sun and the side that's not. And you have to manage that. One side gets too cold, one side gets too hot. So spacecraft engineers have all these little systems that like try to equalize that. But in the case of the James Webb Telescope, you don't want to equalize that. You want the cold side to stay as cold as possible. And you want the hot side to just survive. So we've got all these special materials that have gone into insulating and conducting heat, and these little systems of pumping, like almost like your radiator in your car that pump hot things over to a cold part and it radiates some heat away. And it's just thermal management is a really, really big deal in spacecraft design.
Yeah. And then we also had a question on YouTube. Vince was wondering, how does the telescope get repointed for different areas in the sky? Is the entire rig reoriented, or is there a mechanism in the scope itself that turns just the telescope?
I love that question. That's a super good question because it's going to make me tell you about something that's cool that I hadn't thought about telling you about. There's two ways to move a spacecraft in space. One is obviously use some little rockets. And James Webb Space Telescope has some little rockets, and they have to be used to keep it in the right place in that Lagrange point orbit, like management of your trajectory kind of thing. But if you just want to turn a spacecraft around in one place without actually speeding up or slowing down or going from this place to that place, there's these things called reaction wheels. And they're a lot like they're little gyroscopes that are the little gyroscopic things, which is like a bunch of little bicycle wheels put in different planes. And if you take a bike wheel and you have somebody and you're holding the bike up like this, and you have somebody spin that wheel as fast as you can, it makes it's hard to turn because you get that force going. But if you spin up a wheel like that inside a spacecraft and you turn it, you make it turn, but it's attached to the spacecraft. All that force that you feel trying to turn a spinning wheel with your hand, that turns into turning the spacecraft. So you can use these things. We've done this always. You can use these things called reaction wheels that can turn a spacecraft around to go from pointing at that star to that star real easy without firing a rocket. But without firing a rocket, you're not going to move where it is in space at all. You're just going to turn it around on its own axis.
Very cool.
So thank you for asking that question.
Yeah. It was a great question. Okay, so we are very close to time, so I'm going to read out our last question for you. We had a question. Carol was asking, will some of the images sent from the James Webb Space Telescope be available to the public?
All of them, yes.
All of them. Awesome. Okay, yeah.
And they have to be processed, because they're all in infrared. And once scientists get these infrared pictures, of course, you can't see it. It's just a bunch of digital electronic data. But they know, and this is like how dinosaur doctors at the museum know that this dinosaur walked 30 miles an hour and only ate peaches. They know this, like what you get this signal, they know what the real color is. So it takes a while to get this digital data and convert that back into a picture that we can see and understand.
Yeah, so that's something that, like, general public can be like, oh yeah, that's what that is. Okay.
Yeah.
Cool. Wonderful. Okay. So everyone had awesome questions. I'm so sorry that we didn't have enough time to get to them all. But thank you all so much for joining. I'm going to share my screen really quickly to help wrap it up here. All right. There we go. Okay, so thank you so much, Alan, for speaking with us today. And thank you all to everyone who turned in, both on our Zoom and our YouTube side. We hope you enjoyed learning about the James Webb Space Telescope. And thank you so much to our sponsors, the North Carolina Sea Grant and Pepsi, as always, for our sponsoring our programs today. Sorry, did I say Sea Grant? I meant North Carolina Space Grant. Sorry about that. And then thank you so much to our members of the museum who help make events like Astronomy Days happen all the time. So thank you so much for that. For our Astronomy Days, we have an awesome t-shirt of Venus that is on sale. So if you'd like to pick that up, it's a very, very fun t-shirt for that. It's pictured on the slide here. And there are other really great programs scheduled for today. So our next public program is a little bit of a pivot from Astronomy Days. We have an awesome program about rattlesnakes and you at noon. So that is a really fun public program that'll be on our YouTube. But we also have a program at 2 o'clock that is about human space flight, going back to the Astronomy Days topic. So we'll post the links for our schedule and how to register for those programs in our chats. And we would love to hear if you enjoyed this program or not. You can type that up in the chat really quickly. But also, we will be posting the recordings of this on our YouTube, and they'll be available through our Astronomy Days website. So thank you so much for attending today, and we hope you all have a great rest of your day. Bye.
Bye. Thanks, everybody.
Thank you, Alan. Learned a bunch.